Hello, everyone, and thanks for joining our webinar today. My name is Vera, and I will be your moderator. Before I hand the mic over to our speakers, Arindam Chana from the Qt company and Marcin Lisowski from Sealy Auto, I have a few things to mention. We'd love to hear from you during today's presentation, so please, if you have any questions for our speakers, enter those through the Q&A button. This will be answered in the end of this session. This webinar will be recorded and you will receive a copy of it delivered to your email account later. Now, over to our experts. Auri and Marcin, the stage is yours.
Thank you. Good morning, good afternoon, people. My name is Arindam Jana. I work at the Qt company as a product director, and I'm in charge of the MCU business. Today, we're going to talk about how to drive down automotive costs for creating richer HMIs with Qt for MCUs on the NXP i.MX RT1170. Before that, I'd like to talk about the Qt company and Qt. So the first release of Qt was in 1995. So it's been more than 25 years since our first public release. We have a fairly large ecosystem of 1.5 million developers. And Qt is used across 70 industries with over 3,500 commercial customers. And over the last 25 years, we have also expanded our footprint across the globe. Our headquarters are in Espoo, Finland, but we have offices, multiple offices in Europe, multiple offices in the US, and then in Asia Pac, in Japan, Korea, China, India. And all of these offices, we also have support staff who can support our customers locally. Yeah, during this 25 years, we have acquired a lot of customers, a lot of them in, as I said, across 70 different industries. But if you look into the major industry segments where our customers come from, they are mostly automotive, industrial, consumer, and medical. From our customer survey, we see that our customers are fairly satisfied. More than 95%, the return of investment expectations were exceeded, and more than 80% of our customers find they are more productive with Qt. So what is it that our customers are doing with Qt? They basically created embedded software. As I mentioned, most of our customers are coming from automotive, consumer electronics, industrial automation, and medical. But we have also customers outside of this, for example, in building automation or in agriculture and in also people who are creating standard software, desktop software. But in the embedded space, Qt is kind of the de facto toolkit, especially on embedded Linux devices. And that's where companies use Qt to build powerful software and graphical user interfaces for connected devices. Quality is at the heart of the Qt company, and we are ISO 9001 certified. So we take quality as a very serious aspect during our daily development. We provide a quality baseline to our product, and documentation and transparency in the development processes is integral at the Qt company. As you know, the Qt is also an open source project. So all of these documentation and how the way that the development process is done is fairly detailed. And this is basically a meritocracy-based project development that we support at Qt. But today we're going to talk about Qt on the automotive, especially on the RT1170. People who are familiar with the NXP RT1170 would know that this particular MCU is not just for automotive, but also for industrial and consumer applications. But for today's presentation, we decided that we will be focusing a bit more on automotive, mainly for two reasons. The first is that we have customers who are using Qt on the 1170 already today. And the second reason is that the use case that we are talking about today is how to leverage the two different cores that are available on the 1170. And I believe while we are showing the automotive use case today, it can also be something that can be shown or that could be useful in other scenarios, for example, in an industrial scenario or also in a consumer scenario or even medical scenario. So I think that use case is something that can go across outside of automotive too. So if we look into the different screens that are available in a car, it's not just the head unit and the instrument cluster, but we see screens appearing in a number of different places. For example, the HVAC control is becoming more from a knob-based to a display. We have e-mirrors, we are talking about rear seat entertainment, as well as passenger side entertainment. So there are a number of screens that are popping up these days in the car. And some of these would, of course, be run by or driven by high-powered SoCs, but not some of these, because of cost factors, would make sense to use an MCU to drive the HMI. If you look at what are the different SoCs, NXP automotive SoCs that are supported by Qt out of the box. So we have the RT1170, the i.MX the 7 and the 8. Today, of course, we are going to talk about the RT1170, which is the one which was recently launched. It was already announced a couple of years back, but launched publicly around the Embedded World timeframe in February by NXP. And that has a very silicon GPU. And as I mentioned, it comes with 2 cores, a Cortex M7 core and a Cortex M4 core. So what is it that Qt provides on the 1170? So what we provide is a very tiny footprint, is a very optimized rendering engine, which we call the Qt Quick Ultralite rendering engine. It delivers high graphics performance by utilizing the available hardware accelerators on the RT1170. And as I mentioned, it's got a very tiny footprint. When I say tiny, it's compared to graphics engines that are on high-powered SoCs. So over here, the Qt Quick Ultralite graphics runtime consumes about 80 kilobytes of memory, so RAM, and allowing the rest for application usage. We also provide a highly optimized font engine that can scale up text, dynamic text, high quality dynamic text easily, so that you can ditch bitmap headaches and quickly expand to new markets with non-Latin characters and advanced support. So the RAM footprint, the runtime RAM footprint of this font engine can be as low as 20 kilobyte. We support multiple languages. We have larger character sets and can also support different font sizes. So you can maintain the UI performance even on the most constrained device. We also provide a number of UI controls as templates so that you can directly start creating your user interface without having to create something from scratch. But of course, all of these are, as I mentioned, are templates, so you can also create your own custom controls fairly easily with these templates. On top of that, we also provide tools for both designers and developers. So what we are seeing these days are that designers are getting a lot involved in creating the graphical user interface on embedded devices. So we provide tools where designers can import their design assets from tools like Photoshop or Sketch or Figma into Design Studio, which is a tool provided to designers. And there they can design and implement UIs, create animations, add animations, and validate on these designs on the device prototype. At the same time, the developer can take these designs from the designer and write the backend, integrate, and for example, add the backend and application logic and test on the device. So this gives a really nice, speeds up the development process since designers and developers can work in parallel. one of the big advantages that we are seeing with Qt is that our customers can scale up from microcontrollers to microprocessors. So the applications that are created on the RT1170, for example, can be easily scaled up to the i.MX 6s and 7s and 8s. So this is something that is easily possible because Qt is a true cross-platform framework. And with the model view controller paradigm that we provide, it's easy to separate the GUI code from the business logic. So we can easily scale up the GUI code on different devices while integrating existing business logic with this front-end GUI. With that, I would like to hand it over to my colleague, Martin, who will talk to you about the HVAC application on the 1170. And yeah, please take over, Martin. Thank you.
Good morning, everyone. Well, yeah, so good morning, everyone, again. My name is Marcin Lisowski. I'm a software engineer at Silly Auto. I'm also part of Qt MCUs team, which develops this product. Today, I will tell you about how we at Silly Auto think about the problems in automotive industry and how we solve them. As an example, I took HVAC control demo with dual core architecture in it, which we have made in the last days. First of all, we have to understand the challenges. So let's look on the three major problems. Automotive solutions are usually built on complicated hardware. This requires a lot of work to set up different components together and make dedicated software for it. Safety critical parts of the system has to be certified, and if we will run them next to non-safety critical components, they will have to be certified too. This usually causes additional development time, what of course drives the costs. Before we designed the solution, we wanted to really feel the problem. So we decided to implement the real case scenario. Our goal was to create a digital HVAC control as a data source, which is CAN bus, which provides the state of the user interface, like temperature or the fan speed. We also didn't want to run CAN component together with the UI part to avoid additional potential certification. Of course, from the performance perspective, we expected to run the app with 60 frames per second. So how did we prepare for it? At Silly Auto, we choose two main parts on top of which we built our solution. We picked new automotive microcontroller, NXP 1170, which has two cores, Cortex M7 and M4, and a powerful GPU to accelerate graphics rendering. And to create advanced UI, we needed a framework which could run on this board. We needed something which is efficient, quick to set up, easy to use, and provides a way to create advanced modern user interfaces. So that's why we choose Qt MCUs. From the hardware side, 1170 gives us a way to distribute safety critical part of the system and UI components between two cores, so we can be sure that we won't have to certify the UI part. Also, as I said, it comes with dedicated GPU, which is able to accelerate basic graphics operations and complex transformations as well. So at the beginning, we had to prepare architecture for our HVAC. So we went through the hardware features and decided to use Cortex M4 for CAN communication. It is responsible for handling all data frames that comes to the device. Then it passes frames through the shared memory. On the diagram, you can see that marked with the yellow. And it passes those frames through the shared memory to the Cortex M7, which is running Qt MCUs. Also, as you can see on the diagram, Qt MCUs is delegating all of the rendering to be dedicated to the GPU. It's by utilizing the Ultralite APIs. Well, so how did we start it? As I mentioned, we selected Qt MCUs as a graphics framework to render our HVAC user interface. And Qt MCUs comes with support for NXP 1170 out of the box. So to bootstrap the project, we just had to compile one of the existing examples. So we did that. So after a few hours, we had our setup ready, and we were ready to start developing the UI directly on the target device. Also, Qt contains all of the code to set up the board and initialize the hardware, so we didn't spend the time for looking into the documentation and specification of the hardware. After a few days, we had our UI ready. Previously, we agreed that application has to run with constant 60 frames per second and has to consume minimal amount of memory. Some of the features from Qt makes it possible. So let me focus on a few of them to let you know how this helps us. So to reduce assets memory consumption, some of the textures are converted to alpha maps. This image format keeps picture pixel format information on only 8 bits. And in our case, we are using them for elements which are changing the color. Texture map contains information about the pixel transparency, and Qt for MCUs keeps the information about the color. During rendering, the texture and the color are passed to the GPU to make colorized image as an output in the frame buffer. Hopefully, we don't have to think about communicating with the GPU, as all of the work is done by Qt for MCUs under the hood. QML code implementation, which defines the UI, is that simple as you can see, and implicitly covers hardware acceleration. And as whole rendering is hardware accelerated, I have to mention about transformations as well. Any kind of rotation, scaling, or even perspective transformations is done on the GPU. So we didn't encounter any bottlenecks here. The only thing we had to do is to write the QML code to define our UI. If one would like to rotate some texture, is that simple. Few lines of QML code will make it happen on the GPU, and finally it will appear rotated on the screen. Just because Qt does all the hardware acceleration under the hood, we are able to finish our UI part within 2 weeks. Qt reduces complexity and time required to create user interface. And besides those features I just showed you, there are more of them, and you can utilize some hardware components like LCD interface version 2, which provides you a way to make use of the hardware layers, which are also a thing that could save you some memory on a device or improve the performance. Well, once we had our UI ready, there was a time to run a secondary core. Our Cortex M7 was designed to start with Qt. As a first core, we had to start Cortex M4 from there. This means we had to compile another application separately, built especially for the second core, and wrap it inside the Cortex M7 binary. That was rather a simple task, as NXP has prepared a great software development kit, which contains a bunch of examples to show how to use particular features, including multi-core examples. Once we prepared a wrap binary, there was a time to power on the secondary core. And here is the moment that I have to mention about 2 of the libraries that are delivered together with the 1170 SDK. First of those 2 is the MCMGR from the left side, and this library can be used to manage your secondary core lifetime. So this library provides you a way to start up the secondary core, to stop it, to check its state, to exchange some basic informations in which we can compare to the, for example, the enum value that is exchanged between the cores. So this library is basically designed to maintain the lifetime of your secondary core and to communicate with the basic informations about the events that are happening on the both cores. And the second library that makes our solution possible and easy is the RPMSG library, which is used to exchange some more complex and structured data between 2 cores. And about this one, I will tell a bit more later on. So let's focus on the MCMGR library. So as I said, it's a library which in our solution is used to manage the secondary core lifetime. So on the Cortex M7, which is our primary core, we are using 3 of the functions that are available in this library. And as you can see, it's for initializing this library and also to start the secondary core. On the Cortex M4, we are just using a single function from this library to retrieve the startup data. What is the required step to pass the secondary core wake-up process? On the left side, on the left bottom side of the slide, you can see rest of the functions that are still there and can be used to create a rich application that is utilizing the 2 cores and to provide the rich lifetime management for it. And As a short example, I can show you the code that is booting up the secondary core. On the left side, you have the Cortex M7 application main function. It's a simplified version with some pieces cut off to not waste the space for it. So as you can see on the left side, Qt does all of the platform initialization. As a second step, we are retrieving our wrapped binary from the flash memory, and we are copying it, in our case, into the OCRAM. And just after copying the secondary core binary to the OCRAM, we are waking up it by calling the start core function from the MCMGR library. And on the right side, we have the Cortex M4 main function, which will be called just after calling the start core function from the MCMGR. And we are just doing a basic initialization here, and we are retrieving the startup data, what is, as I said, the required step to finish the waking up process of the secondary core. Well, so at this point, we have our architecture partially implemented. So we have everything from the Cortex M7 to the right. So we have Cortex M7 running the Qt, and we are accelerating the UI with the GPU. We have also the left side. So the Cortex M4 is running on the device, basically, as Cortex M7 is starting up it. So, well, let's look how we implemented the two remaining parts, so the CAN and the shared memory components. So let's focus on the CAN controller implementation. So once again, 1170 SDK from the NXP comes with the full solution for handling the CAN controller, which is embedded on the device. So and the only thing we have to do is to use the Flex CAN driver for it, which has a bunch of the functions to receive, to send, to prioritize the messages, and to implement the whole loop for handling the data frames that are coming through the CAN bus. So just what we did, we just wrote the simple wrapper for the FlexCAN driver, and we were able to retrieve all of the informations directly on the Cortex M4. And to be honest, Cortex M4 is smarter than that. So Cortex M4 can be used as your backend for whole solution, for your whole application. So you can implement the safe renderer there, which will check for the graphical components if they're still present on the screen. You can still create the wireless connection and implement all of the logic behind that on the Cortex M4. You can handle the Ethernet connection and other peripherals as well. So Cortex M4 and maybe the secondary core can be used for all of the things that are happening behind the UI and which are not visible at the first glance. So dual core architecture can split your whole solution to the safety critical things and non-safety critical things, or even you can create a backend with a secondary core. Well, so right now we know how Qt works on this board. We know that it's accelerated. We also know that Cortex M4 is running as a secondary core and is able to retrieve the data frames from CAN. So how to exchange the informations that are coming through from the ECU and through the CAN bus to the Cortex M4, and how to pass them to the Cortex M7. And here is the second library, and we are just right now getting back to the RPMSG library from the NXP 1170 SDK. And to be honest, it contains a lot of the functions and a lot of the mechanisms to exchange the data, but all of the synchronization, all of the exchange logic is already implemented there. So we didn't have to spend the time, and we didn't have to know a lot about exchanging the informations between two cores and how the shared memory is implemented there, because all of those things were delivered together with the board and with the hardware as a software development kit. So on the Cortex M7, we just created an endpoint by just calling one function besides few initialized functions. We just created an endpoint to which we sent the structurized messages from the Cortex M4. And by structurized, I mean really structures, C++ structures were just directly exchanged between two cores. So RPMSG library really saved us a lot of time during the development and comes with a verified solution that could be used to build some application and the whole system on it. So as you can see, we are also benefit from the 1170. From the hardware side, MCU is cheaper, so there is no need to spend a lot of money for buying the expensive hardware. And from the other side, 1170 SDK is well prepared for creating a solution on it. So we didn't spend the time, and we didn't think a lot of how to implement the basic functionalities on this board, as everything was already prepared. This, of course, reduced complexity, and this in result reduced the time and the costs. Let's focus on all together once more. So we are sending data through from the CAN bus, and the FlexCAN driver. It's helping us to retrieve those frames on the Cortex M4. And then by using the RPMSG library, we are passing those frames and those informations through the shared memory to the Cortex M7, which is also receiving the frames and those data structures by using the RPMSG library. And then on the Cortex M7, sorry, is passing those informations to Qt MCUs by using the Qt event queue and by using the C++ models that are connected directly to the QML code. And then Qt does all the work for us with refreshing the UI, which then is fluently displayed on the screen. So by building this solution, we achieved the less complexity of the whole application. So we used already prepared components and combined them together to create the fully working application. We did that fast, so the development of the real case scenario will be also shorter, and this will drive the costs, which will be, of course, smaller if the development time will be smaller as well. And that's it for today from me. Thank you very much. And I am passing the voice to Ari again.
Thank you, Marcin. So yeah, let's come back to the presentation. Right. So we created a couple of additional information slide decks here for you. The first one is that we have a number of trainings that are scheduled. So there is a training on the microcontrollers for NXP. So that covers the RT family, i.MX RT family in June, from June 8 to 9. Then we also have 2 other trainings on ST Micro and Renesas. And we are offering 100% off on the $350 early bird pricing for our webinar attendees. So if that's interesting for you, please feel free to reach out. There will be more information in the follow-up email after this webinar. We also prepared another slide deck that has all the useful links where you can download different MCUs, the resources where you can avail different webinars and white papers, and the documentation page itself. And there is a link to where you can download pre-built demos directly onto the hardware and run them without having to install any other software. And now we are let's open up to the question and answer session. So there was already a question in the chat from Ernesto regarding if RT1170 is qualified for industrial usage. I have shared the data sheet from NXP, which basically provides a temperature range. And I cannot speak for the 10 years, what sort of support they have. Maybe it's better to ask somebody from NXP on that part. So there is a question from where can I download the Qt SDK for the i.MX RT1170. So that's basically, I've provided the link over here in the slide deck, which will be shared with you later on. So you can directly download from our website at qt.io/download. Is vector graphics supported in Qt for MCUs on 1170? I'll let that be answered by Martin.
Sure. So vector graphics is supported on 1170 in Qt for MCUs, and I'm just writing the answer with a link to the documentation where you can start looking at the PAF QML APIs, which are implementing the vector graphics for Qt for MCUs and for the 1170 as well.
Thanks, Martin. Then there's a question from Max. Could you please share how you read the shared memory and created signals for the UI from changed data? So I'll leave that to Martin to answer that.
Yes, sure. So to read the shared memory, basically you don't have to do anything special than using the RPMSG library, as all of the stuff that is reading this memory and writing to this memory is embedded inside the RPMSG library. So basically you don't have to do that manually. The only thing you have to do is to provide that piece of the memory and tell the library where is the shared memory. So from NXP 1170 documentation, you can read the addresses of it and pass that information together with the size of how much shared memory you will need, and then the library will do everything for you. Of course, if you want, you can access this memory directly, but it could be a tricky thing, as in between the cores you can lose the information about where you have to read and to which place you will have to write. And the library is also providing you a synchronization, so you know when one core stopped writing to the shared memory and where, and as well on the secondary core side, you have the information that data is ready, and right now you can read the properly written data there. And answering the second part of the question, how to connect created signals with, I don't know if I understand the questions properly, but to connect the informations that are coming in between cores, we are using the Qt event queue, which is processing the informations during the application loop. So once you put the informations in the event queue, it will be visible for all of the Qt elements and directly in Qt through the C++ models. And these have to be implemented by using our subclasses, which are also delivered with Qt for MCUs.
Okay, I think we are running out of time. Was there more questions?
There are a couple more questions. So Martin, would you take those two? I think.
Yeah, I think we have time for one more question.
So maybe let's pick, this one is kind of interesting. So let's pick these. So is it kind of possible to have Cortex M4 code written in C and Cortex M7 in C++? Yes, it's possible. It's simple as that. It's just a matter of compiling it with a different language.
Great. Okay, and if there's more questions, those can be then answered after the webinar. but that's unfortunately all the time we have for today. Now I'd like to thank our Indam and Marcin for the great presentation and everyone for joining. Like I mentioned, this webinar will be recorded and you will receive a copy of it delivered to your email account later. But if you have any more questions, please contact us on info@qt.io. Thank you and have a great day.